Okay, measuring the number of dominoes, the position, and doing just a little bit of simple straight line stuff, we figured out that the net force when you displace from the equilibrium position, whatever the equilibrium position is, assuming the rubber band acts the same at different lengths, which is not really so, but it's a reasonable approximation, okay? So there's plenty of error, though, in that. We're not expecting more than two significant figures of precision, and we'll be glad if we get even close to that, okay? But it's going to corroborate everything that we're talking about. We've determined the net force is about negative 1/7 of a domino per centimeter multiplied by x. Dominoes don't even have the same mass. Some of them are skinnier than others. But this is still going to work out, and I think it's going to work out really, really well. Okay, so a domino weighing 6 dominoes, we got 59, or 4 dominoes, we got 59 grams. So I just kind of rounded that to 15 grams per domino, and then I fudged a little bit, call that 0.15 newtons, because that's how much force gravity exerts, which is then how much force the rubber band has to exert to hold the thing still, right? So we get this, and here's our vector equation. We have a negative here because the force exerted by the rubber band is equal and opposite to the displacement from equilibrium. You pull it this way, the force, rubber band force is back this way. So we take that 0.15 newtons per centimeter, which is dominoes per centimeter, and then we replace the centimeter by 0.01 meter, or do a conversion by some other method, whatever you prefer, trivial once you get used to it. And we get 15 newtons per meter times the negative 0.143, which gives us negative 2 newtons per meter times x. I thought that was low, but then I thought about it a little bit. Okay, yeah, that's plausible. Because we stretched the thing out 1/4 of a meter with just a 60-gram mass, right? Okay, so 2 newtons would correspond to a 200-gram mass. So it's in the right ballpark, so that's okay, we're going to live with that. Not greatly accurate. Okay, well, this equation then says F net is this, which means mass times acceleration is this, which means mx double prime is this. And I took the arrows off of F net and x because you can always let your x-axis be whatever the line of the domino is and put the origin wherever you want to, except you want to put the origin at the equilibrium point in this case. Okay? So this works. You don't need the arrows anymore. In general, if you do this in 3 dimensions with weird materials, you do, but that's a whole different topic. Okay. This is in the form mx double prime equals negative kx, which we saw a long time ago. And we rearrange that x double prime negative k over mx, and we verified that this is a general solution. It's got 2 parameters. Since there are 2 derivatives here, you want 2 arbitrary parameters. And we chose those parameters to be phase angle and amplitude, and by the magic of, just basic high school trigonometry, which you know quite well. We verify, if we take 2 derivatives of this, that we get negative omega squared times this. If omega is the square root of k over m, that means we've satisfied this equation. Okay? Well, now, that means